Okay, so, well, I'm one of the organizers, so I guess I'm supposed to thank myself for being up here. But thank you everybody for coming. It's very strange to be having an in-person workshop after all this time. I'm glad it's finally happening again. So I should say, after those two wonderful talks, which were very oriented towards real experimental systems, I should have asked my student TC to go next because he's going to be talking about Meissner effect and skin effect that you could see in a topological superconductor. This is a much more theoretical talk, but it's a talk about the interplay of disorder and Majorana surface states if you have them. And until we have a bona fide topological superconductor, so I'm going to be talking about surface of topological superconductors, until we can find such a material, this is only purely theoretical with one small caveat, which is that the final punchline kind of looks a lot like what you see in BSCCO. I'm not going to make any strong claims there. I'm not claiming that BSCCO is topological. Right, so that's the title, spectrum-wide quantum criticality. Uh-oh. How do I advance my slides? Why am I locked? Okay. Yeah, can I go backwards? Okay, it wasn't working for some reason. All right, yeah, so the work is all published. There was a PRL first in 2018, actually by Saeed Garashi, who's in the audience, when he was at University of Houston. Then there was a PRX in 2020, and some more work, and then we have a review in Annals of Physics. So most of this work is purely numerical, and so like I said, Saeed was really the innovator here with our first 2018 paper. And then there's been subsequent work by Bjorn Sibirski and Jonas Karcher. And then I had a little bit of help in terms of trying to make some analytical progress with my former students, Yunsheng and Seth. So this is a talk about disorder in topological phases and what does it mean to be topologically protected. So let me remind you of the one case that we actually understand, and that's the quantum Hall effect. So the toy version of the quantum Hall effect is you make your magnetic field infinitely strong, and then imagine you've got some charge impurities in the sample, so you have some rugged potential landscape. And then imagine we fill the system by tuning the gate, right? So at very low densities, so in the limit that the magnetic field is infinitely strong, the eigenstates are just equipotential contours, right? So if I have a very, very low filling, then I just have rare lakes, and those states are just completely Anderson localized in a kind of trivial way. And the system is a vegetable. There's no conductance whatsoever at zero temperature. But as I raise the filling level, eventually I reach the critical percolation threshold where travel by land or sea becomes equally probable or equally easy or difficult. And at this one special point, this is the critical point, it's a percolation transition. And when you study this problem numerically, you get a longitudinal conductance, which has a broad distribution, but it has an average value of order e²/2h. Then if I keep raising the filling, I move off of bulk criticality. So now again, my eigenstates are just closed equipotential contours, now circling rare hills. But of course, there's a crucial difference between here and here, which is that since we've gone through this percolation transition, exactly one state has peeled off to the edge of the sample and is now a chiral edge state, which is circling around. And so if we measure the Hall conductivity, we'll now measure e²/h, because we've got that one chiral edge channel. Now, this is a cartoon. What do the states at the percolation transition actually look like? Well, we believe, so here's the answer. This is a numerical simulation by Ferdinand Evers in some very large system. And so the states are very random looking, right? So there's zero sort of almost everywhere, but they have these rare clusters of peaks. So this is not a plane wave state. It's not an Anderson-like state. It's a critical state. And the remarkable thing about such a state is that actually we believe that the statistics of the state are universal. The state itself depends on the disorder realization and details. But if I just characterize the level sets of this crazy looking wave function, you get actually a universal set of statistics. And technically, we believe this is governed by something called the logarithmic conformal field theory. These are versions of 2D CFTs that we don't understand very well. Okay, so this is the normal situation, right? So in order to get criticality, quantum criticality in this case, in what we would now call a topological Anderson insulator, that's what the Hall effect is, you have to fine tune the Fermi level so that you're sitting right at percolation. So what I'm going to show you today is a purely theoretical model of topological superconductor surface states completely different situation. So it's a situation where criticality appears to occur over a wide swath of energies without any fine tuning. Okay, and so the picture you should really have in your head is I have a stack of these critical wave functions. And in fact, they're going to be exactly the wave functions that sit at a quantum Hall plateau transition. So I'm a theorist, so if you start thinking about materials, you're supposed to think about the periodic table. But all of my favorite papers published in Nuclear Physics B, so I don't know what to do with this. I don't like this table. Ah, that's better. Okay, so this is the classification table of topological insulators and superconductors. And there's many of our friends in this table, but I'm only going to talk about 6 of them. So at top, there's 3 different classes called CAD. These are all topological in 2 dimensions, and they can all be thought of as versions of the quantum Hall effect. So there's the quantum Hall effect we all know and love and actually measure experimentally. That's the class A quantum Hall effect. That's a quantum Hall effect for charge. But in principle, there are 2 other versions of the quantum Hall effect that could be realized. There is the spin quantum Hall effect, which would occur in a D plus IE mean field superconductor. And then you would have pairs of chiral edge states spin up and spin down. You could measure a quantized spin current. And then, of course, the more famous one is the thermal quantum Hall effect, which is supposed to happen in a, say, spinless or spin polarized P plus IP superconductor, where you have a Mayer on a edge node, which carries only heat. So roughly speaking, you could think of these as spin, charge, and heat versions of the quantum Hall effect. Now, the key property of all of these is that if I'm in the topological Anderson insulating phase, then I have these edge states. And the key point is that the edge states exist throughout the bulk gap. So for example, if I have a Chern insulator realization of this thing, then I have edge states that exist on each side of the sample. And nothing can, if I think about what disorder or interactions could do, they can't do anything, right? Because I've got this mode that propagates only in one direction. It can never backscatter unless it hops all the way across the sample and becomes a left mover. So all of the states in the gap are protected, not just those at one energy. So now let me remind you or introduce you to 3 other classes which are probably not so familiar. So in 3 dimensions, there are again 3 phases with integer valued winding numbers. They're called C1, A3, D3. They would all be naturally realized as topological superconductors. And again, why 3 different versions? Well, again, you could think of them roughly speaking as spin, charge, and heat. So in particular, if you had something like a 3D version of the cuprate, so some non-S wave superconductor with light elements, such that you have spin SU2 symmetry, that would be class C1 if it's topological. On the other hand, if you have strong spin orbit coupling, then you have class D3. This is what we believe helium-3b actually does, although it's not a solid state system. And then in between, there's some other funny class A3. That would be like a spin triplet superconductor that has a remnant U1 spin symmetry. And so, okay, who cares? Well, a lot of us care. We would really much like to see a solid state superconductor, topological superconductor. So the question we wanted to ask here is, are these surface states topologically protected? So imagine we get one of these things in the lab. Now it's a very different situation from 2D topological phases. You don't just have chiral edge states that only go in one direction. You have 2D surface states. And these surface states, now the particle, maybe there's a suppression against perfect scattering, but it's not just perfect backscatter. It's not just pure backscattering that protects you from Anderson localization. You can scatter of all, you can scatter at many different angles and still end up getting quantum interference that localizes you. So we asked this question conceptually: what happens if I look at generic surface states of these models of topological superconductors? So in particular, I want to ask not just about the properties of the zero energy state, which turns out to be very special and is protected, but if I just look at all the states below the band gap, are they protected? And there's a conventional view, which you may not be familiar with unless you're an Anderson localization person. But for example, you can go to this review, and the claim is that whenever you have a non-standard class, so something special that is particle-hole symmetry like a superconductor, when you look at finite energy, that goes away. And now you're back in a Wigner-Dyson class. And most Wigner-Dyson classes in 2D localize, right? So if I have my exotic topological class C1 superconductor, its generic surface states will be in the orthogonal class. They all localize. They go away. There's no way we know of detecting orthogonal class states in 2 dimensions. Class A3, you would go to the unitary class. So again, unless something crazy happens, like you tune yourself to the quantum Hall plateau transition, states localize. And then in class D3, maybe the one that's potentially most experimentally relevant, well, generically, you would expect weak anti-localization, and so things should depend on details. Yep. That's right. This is only strong topological superconductors. Yep. Finite energy surface states. So below the bulk gap, but above zero energy on the surface. Any state, yeah. So the point is that you've got a state bulk gap, and then you have a bunch of states in the gap, right? So according to this conventional view, topological protection isn't worth much. It protects maybe one state. So in the case of class C, it would protect one zero energy state, and everything else would be localized. And in fact, even if you look at what interactions do, you would actually expect that one zero energy state to actually go away too. And so it seems like maybe topological protection is just not meaningful. But that's right. So with topological insulators, you're always in the symplectic class, and there is a new wrinkle. There's a topological term that seems to prevent the symplectics, the ordinary 2D metal insulator transition from occurring. But so in that case, you can sort of hand wave it away immediately because you have strong spin orbit coupling. You're going to have at best weak anti-localization for weak disorder. So this should be stable at all energies because they're all in the symplectic class. So here it's much weirder. Most of so in C1A3 we would expect almost all the states to immediately go away with any disorder. And so we thought, well, that's weird. What is topological protection worth? And so we conjectured something crazy, which is that, and okay, I won't go through the theoretical details, but based on the random matrix classification, you can ask, well, is there any way I could avoid Anderson localization? And the answer appears to be yes, just based on replica symmetry. You could have something completely crazy happen, which is that take any generic finite energy surface state. The only way it seems to be able to escape localization is if it sits at the plateau transition of the corresponding quantum Hall effect in 2D. So for example, specifically in class C1, this seems like something easy to test. We're either going to find states that are Anderson localized, or they're going to be critical with statistics that have been well investigated numerically. Same thing with class A3. We're claiming you're going to get a stack of integer quantum Hall plateau transition states. So, I didn't think this was really work. And let me say something very quick about the models. So most of the work that we did, although we've done a little, so most of the work we did was on pure surface models. So for example, in class C1, we took the simplest one where you have two surface valleys, and the only disorder that's allowed happens to appear in the form of a non-abelian vector potential. That's because of the anomalous form of time reverse that appears at the surface. For class A3, it's a single Dirac fermion with generic symmetry allowed disorder, which is a vector potential. Maybe the most interesting one conceptually actually is class D3. So imagine I have a solid state version of helium-3b, and I have a surface Majorana fluid. So the Majorana fluid can only transmit heat, right? Its spin is out the window, charge is out the window. So you can ask, but it's still a solid state system. So if I bring a charge down and I put it on the surface, how does it couple to the fluid? And the answer is gravitationally. How else could it possibly couple to it? The only thing it has is a stress tensor. So in less exotic language, what does it do? It modulates the speed of light for the Majorana cone. So that's cool. So if we can actually get a solid state version of helium-3b, we can kind of play with gravity. And what the disorder would do is it would come in and it would modulate this velocity in a random fashion. So let me just say something very quick before I get to the results. All of these models came up 20 years ago when people were thinking about cuprates. And the point is the following. So Cooper is a very complicated system, strongly interacting, but let's ignore all of that and just say it's a D-wave mean field superconductor. So then what was shown by Senthil and others is that if you consider scattering between all four of the nodes, the thing Anderson localizes. That clearly can't be what's happening, right? If you're in the cuprates and you have good superconductivity, if you violate Anderson's theorem and just localize everything, you're not going to have superconductivity, let alone high TC superconductivity. However, as was shown in, say, this obscure review by Altman, Simons, and Zernbauer back in 2002, if you restrict the scattering at all, you get an effective model that is topological. They were not known to be topological at that time, but you get multiple, the system breaks into multiple sectors, and all of those sectors are equivalent to topological superconductor surface states. And so maybe the one that I'll just draw your attention to is actually this Majorana case, where the only thing the disorder is doing is modulating the velocity of the Majorana cone. And actually, if you look at Seamus Davis's data and in BSCCO, these are supposed to be maps of delta. Okay, now whether it's the pseudogap delta, the BCS delta, let's leave that aside. But you see nanometer scale inhomogeneity. So if your delta is actually shaking, if it's varying on a nanometer scale, that's going to be an effective source of random pneumaticity for the Dirac quasiparticles. And that's exactly what you would have for such a Majorana surface fluid. Okay, but so now let's go to the results. So one quick thing, so what are we doing? We're doing exact diagonalization in these surface theories. We also looked at some bulk topological models, but the system sizes are limited, so the results are not as good. They're consistent. Oh, so how much time?
Clarification.
Oh, yeah.
Just want to ask.
Yeah.
I want to give you a hard any potential disorder would give you, you're saying, has to give you this velocity.
Yeah. So in the case of the Majorana, if you just write down you take two philosophies. You can say, well, I'm going to write down the energy field theory of the surface, say in the clean case, and then just write down all symmetry allowed types of disorder. The only bilinear that's allowed is the mass, but that breaks time reversal. So then what can you do? Well, you have to start including operators with derivatives, and those are the stress tensor. There's ones that break time reversal and ones that don't. The ones that don't are what we call quenched gravitational disorder, coupled to the spatial components of the stress tensor. But you can also say, well, what if I take a charge impurity and I put it on the surface? You can do this exercise of taking a toy model like helium-3b and actually derive the effect of that single charge on the surface fluid, and it exactly enters this way. So, yeah. So what we're going to do is we're just going to characterize wave functions. And the way we're going to characterize them is by looking at so-called multifractal spectra. So I don't have time to go through this in detail, but this is, for example, what a wave function looks like at a 3D metal insulator transition. It has this highly rarefied structure. And the amazing thing is that although this looks totally random, if you characterize it statistically, the statistics turn out to be universal. So you can take moments of this and characterize it. So this is what we did. And so again, we went initially, Saeed did the calculation for class C1 because all the finite energy states were supposed to be in the orthogonal class and localized. And if we found something else, well, of course, if you're doing numerics on a finite size system, you can always see, it could always be that the localization radius is just, much larger than your sample size. So we looked up to the biggest system sizes we could go. But also, if you see universal statistics, it suggests something else is happening. And so here is numerical data. So this is numerical data in some finite energy bin, and I'll show you population statistics in a minute. So this is something called the anomalous, the multifractal spectrum. The blue curve is the curve that characterizes the zero energy state, which if you're an expert is a Wessamino model. There's a green dashed line, which is the numerical prediction for the spin quantum Hall plateau transition, which again, we don't understand analytically, but it's been studied a lot numerically. And what you see is that the finite energy states that we look at seem to fall very well on this curve. We can also just plot, say, two deltas as a function of system size. So this is a 2n 1 by 2n plus 1 grid in momentum space. So in this study, we went up to about 100 by 100. With subsequent work with Jonas Karcher, we went up to about 200 by 200. And you see these dimensions seem to be converging to these green results. Actually, these two exponents are exactly known for the spin quantum Hall effect because you can map it to some supersymmetric spin chain. So they're given exactly by classical percolation. So we don't see any evidence of Anderson localization, and we seem to see spectra that match the spin quantum Hall effect. Now, I just showed you some finite energy spectra. You could immediately raise the, you should immediately raise the concern that, well, I'm just cherry picking. I mean, maybe the spectra is just evolving continuously as a function of energy, and I'm just looking at one place and showing you spectra that looks good. So what you have to do is go and characterize the states throughout the spectrum. And so we invented some arbitrary fitness criterion and asked, okay, if the state looks, if I compare the statistics for the state and it looks like spin quantum Hall within some certain criteria, then I count it, otherwise I throw it out. And similarly, at zero energy, there's also a critical state, class C1 state. And so here you see this population statistics. This is the density of states as a function of energy, and increasing the disorder strength. And what happens is that I squeeze out the low energy states until I only have one or two left. But most of the spectrum is matching the spin quantum Hall prediction. And I should say that the spin quantum Hall prediction is weaker multifractality than the zero energy one. So we're increasing disorder, and yet the multifractality is getting weak, and more of the states look like spin quantum Hall plateau transition. We then did, this was work with Bjorn Sibirski and Jonas Karcher, where we looked at multifractality and also conductance. And now this is for a class A3 system, so a single Dirac fermion with this special disorder that you'd have at the surface of a topological superconductor. And I'll show you some of the data. So here's conductance as a function of energy. And the blue, and so conductance, what would it be? What am I talking about? It's a superconductor. In this case, it would be spin conductance because there's a U1 remnant of spin symmetry. And so the blue dashed line is the spin conductance of the zero energy state, which is universal. And the gray line is the average conductance expected for the ordinary integer Hall effect. And most of the dots seem to fall on that line, except the zero energy state, which actually sits down here, but we're not showing it. And then until we get to high energies, where in this particular calculation, we start to see more plane wave-like behavior. We actually look at the conductance distribution. So the gray curve is from a numerical study. Again, our curves seem to fall right on top for a variety of energies until we get to high energies, and then we start seeing more plane wave behavior. This is for nu equals 2. So this is a topological winding number nu equals 2. And we basically see the same thing. Why is that important? So this is for the experts. So you can try to make a hand-waving argument that you have the zero energy state, which is protected. It's a Webino model that if you go to finite energy and deform it, if the winding number is odd, you would get a Pruskin model with topological angle equal to pi. But if it were true, then for even winding numbers, you would get topological angle 2 pi, and you'd be screwed. And you would also predict some weird Z2 bifurcation of the universality class. We don't see that. We see criticality throughout the spectrum, no matter what the winding number is. And so finally, let me come to, I have no idea how I'm doing on time. Okay, so almost done, great. So finally, I mentioned again, what if we had a solid state helium-3b? So what if copper bismuth selenide or niobium bismuth selenide, one of these things really is a solid state analog of helium-3b? Maybe the actual surface states are buried below the outer layers of the crystal, and that's why we don't see them in STM, who knows? So again, as I said, if we actually had such a thing, the only thing we can couple to with impurities is actually the velocity. And this is actually a gravitational deformation of the stress tensor for this surface mirror on a fluid. Now, in this case, you would actually expect nothing interesting is going to happen, because actually, if I make this weakly random, so I'm not creating curved horizons or anything crazy, this is a strongly irrelevant perturbation. So if I average over disorder, it's got an extra derivative in it. It shouldn't do much at low energy. But then again, at finite energy, well, I don't know what happens. So conventional logic would say you get the symplectic class. And so I should see weak antilocalization, which means the statistics I see should depend on the disorder strength, not be universal. So these are pictures of what we actually see. So at low energies, so these are, you could think of these as being like LDOS maps that you would measure in STM. So at low energies, we see plane wave-like states. The disorders are relevant. If you look at the density of states, it's linear. It's not deviating from the clean curve. You come up in energy and you get these states which look multifractal. And you can go and characterize them, and they seem to have universal statistics. Now, in this case, we don't know what to compare to. We conjecture that these states may have something to do with the thermal quantum Hall plateau transition in 2D, but this has not been investigated well numerically. So this is just showing you, the density of states and what we call the critical density of states. So again, what we do is we go through the spectrum and look at each wave function and ask, is that wave function critical? Does it match this apparent new critical behavior that we're finding or not within some fitness criterion? And so, for example, this is looking at disorder or an order of magnitude, a range of the dimensionless disorder strength over an order of magnitude. And what we see is that more and more of the spectrum gets critical. So it seems to work better and better. And the other interesting thing, though, is that at low energies, the density of states is still perfectly linear, at least for weak disorder. That's consistent with having, just plane wave states at low energy. So again, I'm not a high TC person. I don't know much about the Coop rates. All I know is that when I look at the pictures, we see something kind of similar to this, meaning that we know that when you tunnel into BSCCO at low biases, you see good quasi-particle interference. What I think that means is that you have a few isolated surface impurities whose only job is to cause enough hard scattering so that you can image the Friedel oscillations. The disorder is really not doing anything interesting. But then as you come up in bias, you start to see these nanometer scale inhomogeneous fluctuations. In fact,
that's consistent with your argument that it should be relevant at zero at low end.
Right. So these are maps that Seamus shows of delta. So he's looking at how the coherence peaks shift around. And again, we can argue, are these superconducting coherence peaks? Are they pseudo-gap coherence peaks? So here's a movie of the actual local density of states, over actually a smaller region than the numerics have shown you. So this is about a 50 nanometer by 50 nanometer region. We could go up, if I sort of roughly convert the scales, we can go up to like 200 by 200. And it goes too fast, but at very low bias, you just see a few peaks. And those are presumably just hard impurities sitting on the surface. And you don't see anything in terms of the electronic structure. That's where you see good QPI, and presumably you have plane wave-like states. But far away from it, you have this very ragged, inhomogeneous pattern. Well, now it's disappeared. Yeah, there it comes back, right? And so, well, we've made preliminary attempts to try to actually analyze this data, but I don't have anything to say about that yet. So in summary, we seem to have found a connection between the quantum phase transitions in 2D topological phases in the presence of disorder and the surface states of 3D topological phases in the presence of disorder. And so in particular, we're connecting the classes that have integer valued winding numbers in 2 and 3D. This is purely numerical. There's no real analytical explanation, although, so I will say that Ferdinand Evers and his group has repeated our calculations now on a bulk 3D model. So it's not just an effective property of just these funny surface models. So it's a real topological 3D lattice model. And he sees the same thing. And my collaborator, Alex Altland, at least in this one particular case, seems to have an argument for this particular model to argue why get this critical stacking. So that should appear sometime. But open questions. So there really must be a topological derivation of this. I've been trying to think of one for a few years now, and I'm stuck. So to me, this cries out for a topological explanation. But the other, just to be provocative, well, if we have these, this criticality of these eigenstates in a superconductor, is that bad or good in terms of the superconductivity itself? So my student Shingai is going to present a poster where we're looking at simpler systems, so one-dimensional systems, but these are funny one-dimensional systems that have spectrum-wide criticality. So the Abri-Andre model and the parallel random banded model, and this is a plot of the enhancement of superconductivity. That's this this white line. That's where delta is largest. We're just doing mean field BCS as a function of U. And the metal insulator transition, where you get spectrum-wide criticality, is this red curve. So at least for weak interactions, these things seem to be tracking. All right, that's it.
Very short on time, so just a couple of questions. Maybe send over.
I actually had a question. You picked out one of the two to answer.
You continue to copy.
Yeah. So because you deal with non-interacting problems, can you try to derive a sigma model for the localization?
Yeah, so right. Well, so in principle, we have exactly what we want, right? So the zero energy states, in particular in class C1 and A3, they're the one CFTs that we can actually solve and predict multi-finite, the Wessamino models, right? So great, I've got a Wessamino model, but then I have to perturb it with finite energy. Finite energy couples the left and right sectors. It's a relevant perturbation that flows off. And so then, what do we do when we try to argue that we're going into another symmetry class in Anderson localization? We guess where we're going, we get out the target manifold, and then say, okay, now I'm in this sigma model. But the point is, like in class C1, if you do that, if you follow the standard logic, you would say, well, I'm in the ortho class, everything must be localized, right? So here we say, well, actually, if you look at that argument carefully, all I know about the finite energy perturbation is that I'm reducing the symmetry from G cross G to diagonal G. But the diagonal G is still symplectic in fermionic replicas. So there's two possibilities. There's class C and orthogonal, and we seem to see class C. And I would also say that, like, it's not completely crazy, right? If you have a purely 2D system that is class C1, like if you have a D-wave model and you turn on strong disorder, then there's a clear argument why everything should Anderson localize in the orthogonal class at any finite energy, because there's no symmetry distinct energy except zero, right? But this is different. These are all bound states on a surface. So maybe the anomaly, the Wess-Amino term can give you something different. But we don't have a good derivation. And the other thing that's a big pain in the rear is that what you're trying to do. So we know where we want to go. We want to go to topological, to Pruskin models with theta terms. But that means you're mining the UV for the contribution to that theta term, and the UV might include the three-dimensional bulk, which is hard. So
I have what I think is a simpler question.
Sure.
And that's basically how to interpret your word stacking.
yes.
Is there really a spatial component? Is there a relationship between, should we really be thinking about these as actual vertical stacks or something?
No.
What
Only it's stacking in energy. So
Energy,
so
okay.
the statement is that at the edge of a quantum Hall droplet, you have a whole bunch of chiral edge states at any energy, right? I've got a band of them, right? And you can really just think of them a band even in impurities, because they just snake around any impurities that you put there. So here, imagine I've got a 3D bona fide topological superconductor, and I ask, how does the surface fluid react to those impurities? And so our claim is that what happens is that it avoids Anderson localization. It's topologically protected, whatever this means, but it does so in this crazy way where every single state looks critical with the same statistics. Like you've taken a stack of, like every state is sitting at the plateau transition of a corresponding 2D topological phase.
Okay, I think with this, let's just
So